Hi, I'm here to talk to you today about solving the right problem. I'm going to talk about a lesson learned from my own career as a mechanical engineer who started off designing interconnect. Now, interconnect can be any form of wiring harness or cable or flex circuit, just about anything that has connectors on it. So I'll talk to you today about a use case that was in a gimbaled system. And let me explain what I mean by gimbaled. I mean that there are certain electronic packaging that go in a gimbal, and a gimbal is a system that can move as I'm moving this scaled model, and it can move this way, it can move this way. There could be different degrees of freedom. So in a system similar to the one that is modeled in my hand, you can imagine that if there's a cable that goes from the platform, which could be an airplane, it could be a tank, it could be any other vehicle, that goes from the platform to the sensor package that moves, then that cable has to be somewhat flexible. Also, the cable has to be secured so that it doesn't rub up against the side of the housing. So one of my first assignments as an engineer fresh out of college was to take such a cable, and the engineer before me had molded an elbow in there. And it was molded like this. This isn't the right cable. This is a common laptop cable. I cannot show you proprietary hardware, and I can't go back in time and grab samples. So I'm showing you things that are similar, that are off the shelf, or that are representative samples, just to get the idea across. So the engineer before me had actually designed a molded elbow into the cable, and that elbow had a plate that would then be fastened onto the system. Well, the plate had taken, hold please. Originally, the designer designed a flat sheet metal plate that would be put on the molded section and then the edge of the sheet metal was coiled into a cylinder so that lacing tape could go through and it could be tied onto a tie down in the system. Well, it didn't bond very well to the plastic, and by that I mean that it came off. When there's not a good bond, it disbonds, it comes off. I tried really hard not to use engineering speak and to talk like a normal person, but y'all, it's hard. So it disbonded, and so the engineer drilled some holes through it so that the molding material could go through and hold that plate on there. Now I looked at that and I got all excited and I said, I know what that looks like. That looks like a hinge. So instead of taking a piece of plate metal and forming it and cutting holes in it, why don't we just buy a $1 hinge and put that on to the cable, and then we'd save a lot of money. If the formed bracket, which again was only half of this, if the formed bracket was $52 and I could buy a hinge for $1, then I could save $51 per unit. I started down this path and I was told, well, we have to look at the materials because only certain materials are agreeable to the customer to go into this platform. That's for a lot of reasons. We don't want to use hexavalent chromium, for example, because that's a health hazard. If you don't believe me, go watch the movie Aaron Brockovich, and it talks a lot about that chemical and similar chemicals. what I'm trying to tell you is that there's a list of prohibited chemicals, and we've got to be careful that we don't put those in our system for various reasons. I did that. I worked with the material scientists to ensure that we weren't using a prohibited material. And then I had to work with a different mechanical designer who owned the next higher assembly to ensure that this bracket wasn't going to have a galvanic coupling with the next higher assembly, meaning that if I was using aluminum against stainless steel, it causes corrosion, galvanic corrosion, because they're so dissimilar metals. So I've talked to a material scientist, I've talked to another mechanical engineer, I've got to talk to procurement about purchasing hinges, because we can't just buy them from anywhere. We can't just go to Home Depot and buy hinges to go into a flight assembly. It has to be purchased from an approved supplier, and so on and so forth. There are structural analyses, there's thermal analyses, and at the end of it, we were using a hinge, and I was very, very proud of myself. So I did a good thing, right? I saved $51 per cable, and one cable per assembly, so $51 per assembly, and I was going to save the company lots and lots of money, and yay, engineering and Six Sigma. Oh, by the way, I did all of this as part of a project to earn my Six Sigma certification within the company I was working for. Well, at the end of it, as I'm patting myself on the back, a more experienced engineer said, "How much money did you spend?" And I said, "What do you mean? I didn't spend a dime." He said, "Oh, wait a minute, but you did. All those labor dollars add up. The hours that I spent researching the problem, coming up with the solution. I had actually visited the supplier, the company that made the cable, and talked to them and performed a whole, we went through a fishbone chart about what was going wrong with the molding, which was another part of the project. And again, I talked to the material scientist, I talked to a mechanical designer, I had to get the program manager to sign off, all the analyses that had to be done. If you add that all up at $150 per hour for an engineer, which is an estimate, some of us cost more than others, and it's a fully burden rate, yada yada, caveat. At the end of the day, I spent a lot of money to save $51 per cable. Now, to continue on that cost analysis, $51 per cable times about 120 units were what we were contracted to make at that time. And if you multiply those out, it was pretty close to a wash. I didn't save any money, especially considering that the next engineer who came on the program ditched the molding entirely and changed to a flat-laced cable. So just had cable ties instead of molding, which eliminated the problem, eliminated the need for a bracket altogether. To which one might say, why didn't I think of that? And I didn't think of that because when the engineer before me turned over the problem to me, he told me the cable needed the molding to protect the wires from getting nicked in the system. Well, that's all well and good, but it wasn't true. So I should have asked more questions about why we needed the molding, about the history of the cable, about where it was being used, and done my own research to understand the problem before moving forward with the solution. Because everything I did was eliminated when the next person came along with some cabling, with some flat lacing. I'm sorry, just lacing cord. And again, this is not the system. This is just a sample so that I can show you the general idea. So the next time you think you have a solution to a problem, I'd like you to step back and really ask yourself to examine the problem and think about the solutions. Have a great day. Oh, and happy innovating.